Okay, we're going to start today, Tuesday, look into filtering for the week. Okay, the next few days we'll be talking about different types of filters, low pass, high pass, band pass filtering. Today we're going to just go over some of the concepts, some of the ideas, what components are used, etc. A few diagrams maybe. And so let's get started. First, we'll open up the PowerPoint presentation. And we'll put it on slideshow. Here we go. Okay, basically this is chapter 26, and we're just going to start with going over sections 1 through 5 of chapter 26, which is an introductory to AC filtering. Okay, basically we're going to define what AC filtering is. We're going to look at some signals. I think we've seen some of it before, but this is a little bit different. Maybe we're going to look at a distribution of frequencies, talk about biasing. Okay, biasing is something that's probably new to most of you. And we'll discuss coupling and bypassing using capacitors to couple and to bypass certain frequencies. So let's define first what electronic filters are. So the type of process filter which in the ways of an electrical circuit using electronic components, okay? And what they do is they remove unwanted frequency components from some kind of a signal that we're picking up. And we also want to enhance the wanted ones. So we basically choose what frequency are we looking for, and for us to hear it, we're going to have to amplify it first, and then do all sorts of nice things to it. Okay, pick out the tone and whatever. So electronic filters can be passive, okay, which means that they're just RC or LC circuits or LR circuits. They can be analog, and they can be digital as well. We could do some digital, which we're not going to discuss in this class, but later on possibly we will, at another class, we'll talk about digital filtering. Type of filtering is high pass, okay, which passes high frequencies, low pass, which pass low frequencies, or band pass filtering, which likes to select a certain very small range of frequencies to pass on through, and preferably one typically. Or we can use a band stop which rejects that particular frequency we want to get rid of. If it's an annoying frequency, such as a specific noise. Also called a notch or all pass. Okay. So basically, we we use either sampling or we use continuous time. They can be linear or they can be non-linear. That's basically the response. And they can be something else which we won't get into, but an infinite impulse response or finite impulse response, which if you're interested in, you could probably get some more ideas from Googling it, okay, looking it up on other means. But we're not going to get into that. Okay, but we are going to tell the difference between a passive and an active filter. Passive filter, okay, because it uses passive devices that don't require extra voltages, extra power, Okay, so they basically are RLC circuits, resistors, inductors, capacitors, and they're called passive filters. Or we can talk about active filters, which use pretty much the same type of components, but with an added components to do amplification. And basically, you can't amplify if you don't put extra power into it. So basically, this is concerns about picking up a small signal, that barely, very weak signal, and then we can filter it, and then we can amplify it using uh, solid state devices. So the principal components that we use in this case are inductors, which inductors, as by now you should know, they block high frequency signals but conduct low frequency signals. So low frequency signals pass right through inductors. Whereas capacitors do quite the opposite. They don't, they block DC, okay? They block DC, but pass uh, AC, and normally they do a better job of passing uh, low frequency responses. Resistors are not reactive, so it's a passive component. Non-reactive, so they don't contribute much to the passage of a frequency or filtering of a frequency. But together with a capacitor or an inductor, they create a time constant which allows you to select a frequency range. Transistors are solid state devices and used to amplify low amplitude signals, and they're basically two types. Well, there's several types of transistors, but the bipolar junction transistors are two types. They're NPN or PNP. Okay, basically the difference is that they each take on a different current level. The operational amplifier, though, is made up of a bunch of transistors, okay, inside, and it's a microchip, often we call it an op-amp, and allows you to use, by using resistors and capacitors and whatnot, to create a suitable amplification. So what is our electronic environment? Okay, what are we really talking about? What are we getting these signals from? Well, obviously we get these signals, electromagnetic signal waves from space. Okay, they are transmitted near or far, and we really are surrounded by radiating EM waves all over the place. So and basically there's a mixture of these. There's mixed frequencies, radio and TV channels, for examples, are really mixed frequency signals. The other thing that's kind of nasty is noise levels, which interfere a lot of the times with what we're trying to actually hear or listen or see. Okay, we get static. We're going to get static on our TV, get static on our radios, usually RF. FM does not doesn't get much static on that. And the other thing is that these frequencies have different amplitudes and wavelengths. So the different radiation types, okay. So the first thing we want to do is we want to select a radiation type, RF or whatever. Then we select the proper frequency or the channel that we want to pick up, or channels that we want to pick up. We want to remove interferences. We want those signals that give interfering, we want to discard them, so we ground them out. So we create a filter that essentially grounds them out so they don't participate. But we also need to transmit the signal. If we're going to be on the airways, we want to be able to transmit it. And if we want to be on the receiving end, we want to capture that electromagnetic wave. So, but when we capture it, let's recognize that it's really low power AC currents that are picked up by our antenna, which is what we use to pick up radiation. So this is an example of a bunch of frequencies. Okay, here we've got a 1 kilohertz 10 volt peak signal, and we could have a 2 kilohertz, okay, higher frequency but lower amplitude, 5 millimeter or 5 millivolt peak, 5 millivolt peak electromagnetic thing. And we could also have a 2 kilohertz, 5 millivolt peak EM wave, okay? So that should be actually a 3 kilohertz, okay? 3 kilohertz, not 2 kilohertz. That's a 3 kilohertz, and you can see that it's 3 kilohertz because it's finer than that is frequency-wise. But that is, and that's actually 15 volt peak, 15 millivolt peak, not 5 millivolt peak, okay? So our antenna will pick up all three of these if we pass them. If they're up there, we pick up all three with 3 amplitude signals. We got a mixed frequency band of signals, okay? It constitutes a band of signals that have different frequencies and different amplitudes. So the pickup is a composite of all 3 of those signals. And that's what it would look like, for example, okay? You can see you've got different peak voltages, okay, and different frequencies. They occur at different timing. So, but we pick up all 3 simultaneously, and we have a composite, a linear addition of all 3 signals. Actually, they're all added together in a linear fashion. So we've got 3 frequency signals, which is really actually a simplification, because normally we got a lot more than 3, just 3 frequencies. We got hundreds of different frequencies to pass through. And so we pick up a band of frequency anyway, just to give you an idea. But there's a need to isolate some of those frequencies from the band, and that requires filtering. So the amplitudes are also very low, as the origins of the signals are usually miles away. So the amplitude, which tells you how weak the signal is usually very small. So if the amplitude is small, then we need to boost up the amplitude, and we use that by amplifying to levels that our electronics can support. And that requires transistors or operational amplifiers, op-amps. After amplification, we can have, we basically add additional power to perform the amplification. So, because you don't get something from nothing, okay? So you've got to add power to boost the power. Basically, functionally, we can look at it this way. This is called functional block diagram where we start out with our antenna. The antenna picks up a signal of varying voltages and frequencies, and normally it's picked up and placed as part of a transformer device. So the transformer itself can boost it up a little bit. And then one of the first things that we do is we can filter out those unneeded portions, the noise stuff. Okay, we filter those out, send them to ground. What we're left with is another signal, a bunch of signals. So now we need a tuning circuit, which actually helps us select a certain frequency or bunch of frequencies. Those frequencies, the tuning circuit signal, okay, is just AC, totally AC, okay. The AC passes through the coupling capacitor and gets amplified. But in order to amplify, we need to add some more power. And that's normally done DC-wise by adding a positive voltage plus VCC. We don't want that voltage to interfere with our tuning circuit here. So that capacitor blocks that DC from upsetting our tuning circuit. And just what you have here is you have a biased signal, okay, that's being amplified and sent along to an output circuit. And our output circuit then actually massages that signal by volume and tone control, which is another frequency type filtering system. So what are the stages? Filtering, we filter first using resistors, capacitor, inductors for tuning specific frequencies. And we amplify stage using a DC biasing, okay, to amplify those weak signals and boost up the amplitudes to get a stronger AC signal. If we use a transistor, we can use either a plus voltage or a negative voltage. That basically, if you're using a PNP or an NPN transistor, that's what that's all about. DC bias is required by the transistor so that you can take that signal and center it so that when you amplify, you know you amplify both the first half or the second half signal of the sinusoidal signal. And basically a sinusoidal signal is what we're talking about. So you want to be able to make sure that you pass both the top half and the bottom half. But the DC needs to be isolated from both the input and also on the output. So we use two capacitors, which haven't shown. So on the passed output stage, then we require additional filtering to adjust for pitch, frequency, and loudness, okay? So more frequency, more filtering is required. So the primary filter types are capacitor, which provide a path to ground, and therefore gives you less attenuation to low frequency signals than to high frequency signals, therefore a low pass filter. But a signal passes through a capacitor, has a path to ground through an inductor, then the filter presents less attenuation to high frequency signals, okay? than low frequency signals, and therefore we call that a high pass filter. So it's a question of the attenuation, whether we get low or high. So looking at the difference between capacitive and inductive filtering, capacitive filter caused by the reactance, which is inverse relationship to the frequency. So as the frequency increases, then the reactance decreases so that you can pass higher frequencies. So higher frequencies show lower ohmage reactance, therefore higher frequency current pass through it. Whereas if you use an inductor, the reactance is directly proportional to the frequency, as we can see by the equation here. So as the frequency increases, so does the reactance. And so the lower frequencies show lower ohmage reactance, and therefore higher frequency currents are therefore attenuated. All right. So have numerous interference signals added to their profile, and most often we want only those clean signals. Therefore, we need to filter out the unwanted interference parts. So we use a low-pass filter. Low-pass filter only allows low-frequency signals, and basically that's from 0 hertz up to some cutoff frequency, which we label as FC, to pass while blocking those that are of high frequencies. Okay. The high-pass filter does the opposite. It only allows the high-frequency signals from its cutoff, from a certain cutoff frequency on higher. So you can have a low cutoff frequency and a high cutoff frequency, depending on what type of filter you have. And finally, we have a bandpass filter, where the bandpass filter allows signals to fall within those two frequency, whether it's a low frequency or a high frequency, okay? So you've got two FCs, one low, one high, and anything between those two passes through, and that's called a bandpass filter. Okay, so tomorrow we will get more specific, and but for now, let's leave it there.